Okay, so good afternoon, everyone. Let's get going. So we have lecture number 15 of the course. And as is customary with me, let's do a very short intro of what we have learned so far. So again, we are with the problem of operator learning. So this is the abstract PDE, and this is the solution operator, which is given here, which takes as input the coefficients A and sources F and churns out the solution U. And we know that because the inputs and outputs are functions, we have to work with this notion of continuous discrete equivalence. Otherwise, we will not be learning the actual mapping that takes functions to functions. We'll only be learning a certain finite dimensional representation. And again, I repeat this notion of Reno, or representation equivalent neural operator, which is that you have an operator that works between functions and functions. And the way you go is you go down to some grid by a suitable encoding, point values, for instance. If you have band limited functions, you do your processing there, and then you come back through some reconstruction. This is some form of interpolation because from point values, you have to read back the function. And as long as this diagram commutes, then we are okay, right? And while using this perspective, we did some analysis and we found that some of them are not Renos, some of them are Renos, and so on. And in the last lecture, we focused almost exclusively on CNO, convolutional neural operator. And we discovered that it has some desirable theoretical properties, and it also works well in practice, right? So let me just start with that and try to so remember that this is your CNO, and the essential bits of CNO were the two operators, convolution and nonlinearity, and both of them had this nice feature that they were Renos. So you have this is the convolution K here, which is and then you have the nonlinearity, which is given here. So in particular, you have to use this upsampling and downsampling operations in order to preserve the band limits, in order to have these Reno properties and so on. And in practice, what we ended up was with a operator UNet, which had this look, or this sort of a multi-scale information processing. So you took in information, lifted it, then sort of reduced the resolution, increased the number of channels, kept on doing that in this sort of structure preserving manner in the encoder part. So this was roughly the encoder, and there's also a decoder, which is on the other side. And we will see also more and more all sort of vision, state-of-the-art vision processors, vision machine learning algorithms, they have this sort of multi-scale feature. This is an important part of the whole thing because it allows for multi-scale information processing. And we showed through various examples that it has also good performance. Some cases it doesn't do better than this is what I did not point out in the last lectures. For instance, if you take Allen-Kahn equation, which is a nonlinear parabolic equation, ut is roughly u1 minus u squared plus some k Laplacian of u. So you have some reaction, which is given by these terms here, or 1 minus u, I forgot the exact form of the nonlinearity, and you have some diffusion, which is given by this term here. Here, for instance, okay, the errors were small, but FNO was still competitive. Remember, so this was one example. In general, there were both these approaches are fairly competitive. And what we should remember is that the main differentiation between them to some extent comes from the fact that one is a Reno. So if you had error versus grid, so in one case, you more or less got a flat one, and in the other case, you got a something like this. So this was sort of the behavior that they had. And this was sort of the major differentiator between them. Otherwise, they are sort of roughly comparable to each other. And one, depending on the problem that you have, one might do better on a fixed grid and the other might do better on another grid. Okay. So now so this is so far so good. Now the starting point of my lecture today is to point out some of the obvious limitations with these approaches. Okay. And to that extent, I have identified 3 issues that we are going to discuss in some detail today, the week after, and the week after, so that you get a comprehensive understanding of where things stand. Well, the first point, which you could have guessed, and I think I said it, is that both FNO and CNO And many of the other algorithms that I mentioned, some of the other algorithms that I mentioned, their sort of principle, even though they don't need it, but their principal mode of operation is always on regular grid. Okay, so in other words, the data, the inputs and outputs and the processing always happens on a regular grid, something like this, right? So this is sort of this is what you allow for, which is okay, right? In many problems we have that structure. Certainly if you have images are always in the form of squares or rectangles, so it's no problem. But in reality, we in scientific computing in particular, remember that we even had the example of the airfoil, right? So we had the example of the airfoil. So certainly the domain there is not a rectangle, even though we reduced it by some masking. If you remember in the last lecture, I had pointed it out, right? So, but this can be an issue if you have very, very complicated grids. So at the moment, at least the way we have learned it, FNO, CNO, FNO, for instance, you can do it on general grids, but then you don't have the efficiency of the fast Fourier transform. Remember, the fast Fourier transform was the key because we had to transform things in the Fourier domain, right? So FNO or CNO, they out of the box, they don't allow for sort of, let's say, irregular grids. For instance, this is a lattice, which is a tensor product of two sort of irregular grids in each dimension, and these are random points. For instance, if you have random sensor locations. So in order to operate with this, you have to do some form of interpolation. In other words, you have to take data here, get back here, take data here, get back here, which is what we did with this masking strategy, right? So we had data which was generated on points in this domain. And then what we did is that we interpolated it onto a regular grid, or we just projected it onto a regular grid and put a mask in order to denote the boundary. So there are some workarounds, and I think if I get time, so in a couple of weeks, I'll probably revisit this topic. But this could be an issue. The second problem and the third problem, they're actually related to each other to some extent, and I will deal with them in some detail. So the second problem is that of time-dependent PDEs, okay? So what are time-dependent PDEs? So if you remember in the last lecture, for instance, we had this example from the shear layer. So the idea there was that we started with some initial data. You will see some examples later today. We started with some initial data, and then the operator simply predicted the solution at a later time step, right? So you had some vortices which were shed. So this was at a later time step. In other words, you started with U0 and you finished at UT. But remember that time-dependent problems, they have some natural sort of a data availability or data, the natural form of them is really in the form of a video. You can think of it as a video, you can think of it as a trajectory, you can think of it as a sequence of images. So there is some information on time, right? So this is what we will look at in some detail today. And somehow intimately related and even more important is the issue of scaling with data. So let me try to just explain it a little bit, and we are going to talk at some length about this today. And next week, we are going to focus on this issue quite a lot. So this is exactly the same problem as before. Remember this Navier-Stokes shear layer problem. So the task is to just predict the solution at time t equal to 1, given the initial data. So I'm taking out the time information completely. I'm saying, okay, you give me an initial condition, and I will churn out the solution at a certain time. This is the setup, right? Now, what I did here is that we took 3 models, CNO, FNO. The number of parameters are sort of comparable. One is more than the other, but this is not a big issue here. And we also took some transformer model, Galerkin transform, some of the early attempts of using transformers in this domain. And the questions that we asked are very simple. That we train the model with X number of training samples. What is the training sample here? This is this pair here, right? So you start with some initial data, and you go to the final solution. So this is, so we start with, so we have for here means we have 2,000, 4,000, 6,000, 8,000, and so on. We increase the number of training samples, and we want to see how the error decays. So the idea is as you give more data, you should get better results, right? So this is roughly the idea that we operate with. And you see that this is actually happening. There is very little theory regarding this. You know, this is what people believe. There is in fact, I was the only one with some results in this direction. Maybe I get some time to describe them in next week. But there's very little theory, but what we observe is that there is some what is called scaling, right? So this is a key issue in machine learning. So you have some scaling. What do I mean by that? The best way is to look at a log-log plot. So here you have the log of the number of training samples. And here we have the log of the, or we have the errors. So it's a semi-log plot, right? So as you can see, now what we do is that we increase the number of samples. It goes all the way from 512, no, 256, 512, 1024, 2048, 4096, 8192. You see that in all the cases, we have some scaling, right? In other words, as you increase the number of samples, the total amount of data that the system is ingesting, you see that the performance in terms of the error gets better and better and better. So more samples. There are some bottlenecks here, and the model size is going to be a bottleneck. We'll talk about that later. But assuming that we have a model that trains, you see that this is the test error, and the test error goes down in a predictable manner, right? It goes down in a predictable manner. In this case, the rate is roughly 1/3. So if you have 8 orders of magnitude more samples, which is 8 is difficult to say, because I don't have 8 orders of magnitude here, but 5 orders of magnitude, you can see that it goes from 8 to 13, and the error goes from like 4.5% to approximately 1%. So it's somewhere between 0.33 and 0.5, right? Because if it would have reduced by 2.5 times, you would have seen that it would be 0.5, but it did not. So it's roughly in that ballpark. So there are some predictable scaling laws. Of course, in this particular case, we see that somehow CNO does better than we also saw that with a fixed number of samples, but it does better than the other models, FNO and the Galerkin transformer. These are very, very comparable to each other, but this one is better. Even double as better, right? So as you can see here, it's roughly 1%, and this is like 2%, 1% and 2%. But what is interesting is that you see the amount of data that is necessary, right? Because, okay, this is not the hardest problem on earth, but even to get 1% error here, whatever 1% means, some number that we fix, some desired level of accuracy, you see that we need about 8,000 samples. And this is expensive, right? Each of this is a CFD simulation. It takes some time. We have very fast code, so this can be done fast, but in general, in reality, you don't have that advantage, right? So each simulation can take, let's say, 10 minutes in 2D. And then you have 8,000 of these. That's too much. So it's already the fact that you need data. There is scaling with data, but it tells you that if you give more and more data, you get better and better results. But how much of data is enough, and what kind of constraints you have with data? Because the difference in scientific computing and in imaging is different, right? Because in images, you just go to the internet and you try to take all the stock images, but here we don't have that. We don't have that advantage. So one has to think a little bit about data. And so this is intimately related in time-dependent problems, because how do things scale with data? Because as you can see in time-dependent problems, we'll have some more data than we expected in some sense. This is what I'm going to teach you. But is the issue of scaling clear? That this is an important consideration, arguably the most important consideration. And this is what I will really focus on in the next lecture. But today, let's focus on the time-dependent problems. That's the main content. So now let me start with some abstract form, because then notation becomes easier. So you start with, this is the abstract form of the PDE. I have taken a first derivative, but you know that first derivative in time here, but you know that second derivative is no problem, because you can always reduce a second derivative into a first derivative or a third derivative into a first derivative by considering systems, okay? This L here is your differential operator. This is a differential operator. And if you want to think of a concrete model, you can think of ut minus some Laplacian of u equal to 0, the heat equation, right? And the initial condition is, of course, u bar, some function. So the idea is that what we're interested is in the solution operator. So this is heat equation, Navier-Stokes, compressible oil equation, Salan-Kahn, wave equation, whatever you want is in this format. Question? No, sorry. Okay, so then what is the target here? What do we want to learn is a solution operator S, and how is it defined? So now you have the initial conditions, because this determine the trajectory, this determine the evolution, but you also have the time, right? The time is a continuous variable. So what you do is that you supply the time, you supply the initial conditions, and you know what is the PDE, then you know the solution at a later time, right? So it's a causal problem. You can always march forward in time, okay? Backward in time is not always possible, only in reversible systems. So now, in particular, what we know is that we can substitute this solution operator is having something called a semigroup property, semigroup. And the idea is that if you, so let's say that you have done the evolution and you can start at a different time and you move further and you get back the same solution. So this is what causality is. And what it means is that you can also put in the time increment here. So let's say that you're starting at, perhaps it's good to do some geometry. So let's say that you have a solution trajectory. I'll just show it in 1D, means not as a video, but let's say that this is a solution trajectory, something like this. For instance, a solution of an ODE, right? And this is your U0, this is your UT. So if you start at U0 and you supply T plus delta T, you will reach this point here. Or you start at UT and you ask what is the increment in delta T, you'll also reach the same point, right? So this is a causality, that whether I start at the beginning and go towards the end time, or whether I start very close to the end time and go towards the end time, provided that the time increment is given as one of the parameters, then we know that the solution can be generated and is unique, right? So this is causality. This means that because it is causal, and we are going to exploit that in some manner, what happens is that the data that you generate, or the data that you record, the data that you observe, is often in the form of trajectories. So what is a trajectory? What is the meaning of a trajectory? Trajectory is not just the value at one particular time, but it's like a video. So you, in principle, you could have the value at all possible times, but of course that would be continuous. We can't store continuous things on a computer, so you have to put some sampling. So it's a collection of time snapshots with the causal arrow being there, means in the sense that at time t equal to 1, then time t equal to 2, time t equal to 3, and so on. So in other words, you have been given, so again, I need to draw some pictures here. So this is time. And just imagine at each time you'll get an image, right? Or a video in general. So then you just choose certain sampling points in time. So this is T0, T1, T2, Tk in general, right? And then T capital K is equal to capital T. This need not be uniformly spaced, okay? This can be whatever your recording instrument, your camera, or your numerical simulation, whatever. This need not be equally spaced. Of course, the equally spaced one is the easiest one. So what you get are this entire set of values. So just imagine that you have all these images in the form of a video, and this has a certain sampling rate, right? So this is the way you can think of it. And this is, of course, given in terms, it's all determined by the initial condition. So given the initial condition and given these lead times, T1, T2, and so on, in principle, we should be able to generate them. So the data that is given there is having this particular format, right? You could also generate it using increments, but that is so for instance, you can go from U0, you can go to U1, and then from U1, you go to U2, then you go to U3, go to T4, and so on and so forth. And when you do numerical simulations, yes, go ahead.
Didn't we have the same setting already prior course when you introduce, for instance, a signal? Because this is also a causal function because it starts from 0 and you march forward in time, right?
Only if you have time dependent, if you have a signal that is static, but it's a function of space, then there is no causality. So the specificity here is the fact that time provides you a direction. If you don't have the direction, there is no reason why you can't go. Just imagine that in this room, I can always walk from here to there to here, and come back. But I can't go to 10 minutes later and come back. Right? So this is where the causality is the key. So time has this causal property, forces causality, and one has to reckon with it. Okay. So now remember that the data is always in the form of trajectories. Let's imagine that we are trying to generate data. We want to go and do a numerical simulation. We take the initial conditions and we do a numerical simulation, right? The numerical simulation automatically has a time stepping. So you generate a delta t, 2 delta t, and so on and so forth. You don't want to store all of it because otherwise it will be too big. You have to sample. So let's say that you store at t equal to 0, t equal to 0 0.1, 0.2, and so on and so forth. So out of a numerical simulation, you will get a trajectory. This trajectory would have some sampling frequency. Let's say that there are k samples in it, or your video has a resolution of 1/k. So you have k frames in the video, right? So these are the two ways you can think about it. And this is the data set always contains that. You have to store it, of course. So the computational cost is exactly the same, because in order to compute later, you have to compute in the beginning. It's all these numerical methods that we also talked about, these are time marching methods. So there is no choice, but you have this information and you put them together, you store them. So there is a cost of storage, but you always have information in the form of trajectories. This is the language of physics. In the language of computer science, this will be videos. Okay, so you have trajectories and you have videos. So what is the learning task for a time dependent? And this is very important, right? Because in a time dependent problem, it is not just given an initial condition and you read off the solution at a final time, because the data that is used to generate this probably has information about the trajectories. And this is something that we need to leverage. Because remember, more data is better. Why is that? Remember this particular graph, right? So the more data is always better. This is somehow the principle of machine learning. So what is the learning task? Learning task, which I wrote in text here, is very simple. Given the initial conditions and the boundary conditions, domain, coefficients, and so on, all the other material properties of the medium, you have to generate the whole trajectory. Ideally, because this is what a numerical simulation does, you have to generate the solution trajectory for all times. Okay, at least for the times that you want to sample, you should be able to generate that. So in a way, this is a harder task. You have data, but our task is also hard. So what I'm asking now is that if I'm given the initial conditions, if I'm given the boundary conditions, the domain, and so on, I should be able to predict the solution for all times in the future, because that is what the solution of the PDE does. So this is harder than what we had seen before, which was given the initial conditions, I wanted a solution at a certain time. Now I'm asking something which is a harder question, that I also need some continuity in time, in the sense that time itself is going to be a continuum. Now, often this issue, and this is important to make a remark here, that this issue is when people who come from computer science and try to do these simulations, they don't necessarily operate within this framework. They say, no, give me 20 values of the trajectory, and then I'll predict the next value. And so they always assume that there is some stream of data that is coming in, and they have to keep on completing the stream. You see, so for instance, just imagine the weather data. In principle, I have access to the weather 6 hours before, 12 hours before, 18 hours before, 24 hours before, and so on. And I could use these guys to make the prediction for the next 6 hours. This is always possible. But this is very special. And it's only possible for like weather data where there is streaming happening. In general, this is not the situation that we are going to work with. Because in general, when you have to generate data for a time-dependent problem, you have to generate it from the initial conditions, like a numerical simulation does. So what is the point of having a numerical solver for the first 50 time steps and then making the 51st or the 52nd time step? Many people do that. I think 80% or 90% of the papers that are written in this field, they assume that there is trajectory data because they're basing everything on the weather. But this is a very, very specific domain. In general, you don't have access to that, right? You are going to design something, you have to set up your numerical solver, and that setup costs are very, very large. So what you would ideally want is that you give me the car and I should read off the flow field. You see? Or give me the material and I should read off how the temperature field spreads. So you should always remember that there is this distinction here, which is very, very important. So for us, we are going to be in the exact situation as a numerical solver, which is if you're given the domain, you're given all the coefficients, you're given the boundary conditions, given the initial conditions, you march forward in time. Okay, and so we want to replicate exactly this problem. Is this clear? The difference between streaming data and the sort of learning task that I have set here, which is harder because you don't have access. You only have access to initial conditions, and then you have to learn. Okay, so this is an important point that I wanted to mention. Now, how do you do that, right? So now we have this, and how does neural operators, what do they do? For instance, what you have learned so far with FNO and CNO, how is this done, right? Well, it can't be done because the way FNO, CNO, the way I have introduced them for you, you don't have that. So far, what we have is that you have a neural operator. It can NO, it could be CNO, FNO, whatever. It takes, let's say, the initial conditions, and it produces a solution at a later time. And to train it, you are exactly using the same kind of initial conditions, right? You always give an image, and then you produce a solution at a later time. So of course, no one stops me from predicting the solution. So what one could do is I could take the kth neural operator. Actually, some people even do that. I can take the kth neural operator, and its task is given the initial conditions. I produce a solution at the kth time level. So the neural operator 1 will produce it at the first time level. Neural operator 2 will do it at the second time level, third time level, and so on and so forth. Then you can use whatever we have, right? Because, okay, it's just a fixed time prediction. I just have what I have, and I just plug it in. Now, what is the issue with that? As you can see, then we have too many models, right? We have to run capital K different neural operators, and this is not the best computational investment, particularly if you want a continuous evaluation, right? Because then in that case, maybe we need 100 neural operators to be able to represent the temporal variation. So this by itself is not going to be enough, for sure. And in particular, as I said, it only gives you discrete time levels. It's very expensive, and it does not give you some data advantages in the sense that let's say I have the trajectory, but I'm not using the trajectory. I'm simply using the fact, so I'm not using the fact that it's a time evolution at all. I'm taking my initial condition, I'm producing the solution at time 1. And this is completely unrelated to taking my initial condition and producing the solution at time 2. I could have used the solution at time 1 to predict the solution at time 2. This is not being done in this naive approach, right? So if you want to take something out of the box, apply FNO, this is a way to go. But this is very, very inefficient, and no one does it, right? So this is just out of the starting point, the starting block itself, this can be thrown out. But this is so we have to somehow introduce time into the scheme. Otherwise, it does not work. So what people do is what I say next, that they use what is called an autoregressive. Maybe you have seen this before. Autoregressive evaluation. What does it mean? Means, okay, this is a simplification. It's a reasonable simplification. Well, actually, you need it in this particular case. So the main assumption here is that you have uniformly spaced time points. Okay, let's say that we have that, just like we had regular grids, we could have uniformly spaced time points. And then the data is given at this uniformly spaced time points. Let me draw a picture. So you have the initial condition, you have the next time point, the next time point, the next time point, the next time point, and so on, right? So what does it do? So what the neural operator does, and as I said, what you can give, FNO, CNO, whatever, what do you do, or CNN, whatever you have, is that you make it predict the next frame. So this, in computer science, this is called next frame prediction. Because now the delta t is fixed, right? I know what the delta t is. The delta t is not so the delta t is the direction here. So what I'm going to do is that I have, I just predict, I'm able to predict the next frame. Similarly, from here to here, I can predict the next frame. From here to here, I can predict the next frame. From here to here, I can predict the next frame. So given the initial conditions, if I want to come to this point, what am I going to do at inference? Is I start with my neural operator. I predict the next frame first. So I go from here to here. That's a neural operator. Then I use that, predict the next frame. So it's like a time marching scheme. Then I use that further. I predict the next frame. Use that further. I predict the next frame. So by using it 4 times, this is what is autoregressively. So also in language, when people model text, for instance, they model it token by token, or roughly word by word, right? So they say I, then there's I am, then something else, then something else. So it uses that context, right? So this is common in language. It's also in scientific computing. It's a very, very easy way. So all that you're doing is that you're predicting the increment of the solution to the next time step. Okay, And so this is exactly what I just said. In formulas, this is exactly this. That if you want to predict a time tk, so what you have to do is to apply it 1 time, then 2 times, and you have to do this k times. So if you do it iteratively, then you are able to evaluate it. Okay, is this clear now? So this kind of autoregressive evaluation, you just keep on feeding the neural operator again and again and again. Okay, so this seems like a very attractive, we will see some numerical examples later. This seems like a very attractive way of doing it. Unfortunately, and many people do it. So this is the most common way in which neural networks are trained and for time-dependent problems. But there are several caveats here, right? So first of all, you need some uniform spacing because it is agnostic to the value of the increment, right? It says that there are equal increments, so you learn something. Second is that you always have, and this process here is called a rollout, right? Rollout is simply, I have a trained neural operator, which has learned to predict the next frame or the next time step. So I just give the solution, the initial condition, and I roll it out. I apply it once, it'll give you a value, I apply it twice, it'll give you a value, and so on and so forth. But when you do long rollouts, particularly during training, remember at the end of the day, we have to train these objects also, right? So the backpropagation algorithm has to take you back to the initial time. Otherwise, how else are we going to do the computation? So while you do backpropagation, this is called backpropagation through time, BPTT. If you have lots of rollouts, then the gradient, you know that each step, the gradient changes. So if the gradient is less than 1, if you do it 50 times, you know, you can get 0 gradient. And if the gradient is greater than 1, then it blows up. So it's sort of, you end up with these problems that you have due to exploding and vanishing gradients. So this is an important element. That's why this you can't sort of do long rollouts during training. So during training, necessarily, you have to do this a whole field, how to do this efficiently. I don't have the time to go into the details. But essentially what you do is that you can only train for shorter rollouts, in the sense that you take 3 rollouts and try to match the solution, or you take 4 rollouts and you try to match the solution. The problem is at inference, you might need to do it 50 times. And this is where this could be an issue. But of course, it's also evaluation only at the discrete time levels. We cannot predict continuously in time. But the biggest issue here is error accumulation. And what is the meaning of that? So let me, without writing in formulas, let me try to explain it in words, what error accumulation is. So remember that we are trying to solve a time-dependent problem, okay? So of course, we start with the initial conditions, and the solution at a later time is going to be very different from the initial conditions, provided that you wait long enough, right? For longer times, just imagine the weather now, and the weather, it was on Monday, for instance, a Sunday. Sunday was 28 degrees, and today is 2 degrees, right? So as we waited long, we saw that there was a huge change. But of course, if you have taken the weather on Sunday and predicted to 6 a.m. on Monday, then this would have been a much easier prediction because there is some continuity there, right? So now just imagine that you have learned only, this is a cartoon, of course, but you have learned only sort of, let's say, summer weather, and so you have made these small predictions. It's okay when you do short-term predictions, and now you have to compose it again and again and again. Just imagine that if you had used weather from last week, because last week was very warm, you would have managed to predict the weather quite accurately on Monday. But then if you kept on using the same operator again and again and again, of course, there is an obvious mismatch here, right? There is an obvious error. So as you try to predict for longer, you are going to get error accumulation because you are making the same operator run again and again and again. Of course, you could have avoided it by, during the training process, having this. But then you have the issue with the long rollouts, that the training is hard. So this is, as I said, means this is a very common strategy. People use it all the time, but it has its, let's say, its drawbacks, right? It has these kind of issues. So you'll see that this is not exactly, this error accumulation is what makes this basically unfeasible. So we need to come up with an alternative, and this is what I am going to describe very quickly, and also in the next lecture I'll give you some more details, which is called, and it's not the only issue, it's not just error accumulation, we also wanted a continuous output, right? We wanted to be able to evaluate the solution operator, probe it at any point. So what do we do? It's called time conditioning. Means it's fairly recent, but there are a couple of papers, including ours, in this direction. So let me describe. And for instance, when I taught it last year, we did not have this. So this is a very fast moving field. So the idea is very simple, that we should evaluate, and also in terms of data, if you remember that the amount of data that you have, you are restricted by the fact that now you exactly have k frames, right? Because you're predicting the next frame, so you're predicting the next frame, so you have exactly k frames in some sense. And then what we do in this lead time conditioning or time conditioning is time itself, just like in the solution operator, time itself should be in the input, right? So it should be an additional channel. It should be in the input. That's already some advantage, because then it allows you to have continuous in time outputs. So you take CNO, for instance, or FNO for that matter, it does not really matter. This is agnostic to the model. So what you could do, the first element is that you could give the time, lead time as it is called, the time to forecast, you can give it as an input. In other words, your solution operator takes time and it takes the initial conditions of the previous image and it churns out the solution at a later time. Okay. And this is usually added as an additional channel, because remember that I have already temperature, pressure, velocity, whatever. So I can always add time as an additional channel. And then after that, so this, in some cases, this is sufficient, because now you have access to a richer amount of data, because in principle, you can say that I can start with the initial conditions and predict up to 0.1. I have the data for that. I can start with the initial conditions and I can predict up to 0.2. I have data for that, and so on and so forth. But in this form, it does not really work, because this is too little an input. Because what happens is these networks have lots of layers, right? And by the time you go to the 10th layer, the fact that you have time as an initial layer or as an initial input is forgotten, because you have to somehow process the time. You have to keep it as a running input somehow, right? And this is done by using what are called conditional normalizations. So let me explain this, and maybe in the next lecture, I'll give you a little bit more detail, because we are really running out of time. So what are conditional normalizations? So remember that in machine learning, and this you have learned also in your practicals, in your tutorials, that you need normalizations. There are batch normalizations, instance normalizations, layer normalizations, and so on. And the idea is very simple, that before you do the processing, so you take let's take a concrete example here. Let's take CNO, for instance. So let's say that you do the processing here, you get an output. Let's say the output is W, another image, right? So what you do is you normalize W, because also the inputs are normalized, because otherwise machine learning doesn't work. The gradients will have very different scales and you can't train. So you normalize. The way in which normalization works in general is that you take some normalization, means that you take your current input to the layer, you take some mean, some expected value. This could be over the batch, it could be over the layer, means all the outputs to the layer, it could be over the instance, and so on. There are different kinds of normalizations. I will tell the boys, Victor and Bogdan, to talk about it perhaps in one of the tutorials. There's no time for the details here, but it's essentially some form of normalization, right? So once you do the normalization, of course, you take out the mean, and then you sort of divide by the variance or divide by the standard deviation. So you want to get things back within -1,1 or 0,1, -1,1 in this particular case, right? And this was the key trick by which machine learning, deep learning architectures work, because without batch normalization and layer normalization, they were simply not working. So you anyway have to do this, depending on the architecture that you have. Like for CNO, you use batch normalization. For transformers, it's layer normalization, and so on. So there is this normalization that happens for the input to each layer. Okay, first you process, normalize, process, normalize, process, and so on. And the idea behind this is, why don't we leverage the fact that we have these normalizations to keep on giving time as an input? Okay, because so that the effect of time is not forgotten. So instead of just giving time once here, you also give time here, you give time here, you give time here, here, everywhere. So roughly that is the idea. And what we do is that we just modify the normalizations. We simply introduce learnable functions. So this could be neural networks, but in general, these are really, so Gn of t is typically some matrix Gn t plus some g hat n, some vector. Okay, so this is a affine function, but it could be a MLP, some small neural network. And what you do is that this gives the effect of time. As I said here, it gives the effect of time at every input, more or less. So every layer remembers that it is doing something for this particular time step or for this particular time instant. Okay, and it's obvious how you normalize it, because how you initialize it, because this guy should be close to 1 and this guy should be 0 at initialization. But of course, these are learnable mappings, so they are going to learn what is the effect of the time for this particular layer at this particular input, right? So this is roughly what the idea is. So you have to give time as some sort of a conditioner, so that you condition the output of your model on the time. Okay. So is this the details about how I take the expected value is not important here. Okay. So this could be that now all the neurons in that given layer produce some outputs, and you could just average over them, or it could be some other kind of some sort of an average. Okay, think of this as some sort of an average, so that you normalize between minus and 1 and 1, and then you're going to modulate this average by this time dependent functions. So the heuristic that you should remember is that in addition to feeding it as the input value, I'm also going to feed it during all layers. So this is sort of the basic heuristic of this lead time conditioning. And I've really run out of time today. I was slower than usual. But on Wednesday, what I'm going to do is that, okay, so now we have this. So the time dependent CNO, what does it do? It has these additional layers, additional inputs and additional layers. And the same with FNO, means all architectures can be modified because all of them use some form of normalization. So you give the input in the input channel time, and you give this within each layer. So now we have this, let's say, new architecture. How are we going to train it? How are we going to leverage the data and so on? And this is going to be the task of the next lecture, because if I start the next slide, I will not be able to finish it. So I don't want to rush it. Okay, so on Wednesday, we start with this, and then we go towards the issue of scaling and transforms. Okay, so let's stop here.